Hello everyone, welcome to my video on semiconductor physics. In this video, we will be briefly discussing about the characteristics of the junction diode. To begin with, let's quickly recall forward and reverse biasing which we have discussed in the previous video. When the P side of the diode is connected to the positive terminal of the battery and the N side connected to the negative terminal of the battery, the diode is said to be in forward biasing condition. The application of a forward bias potential makes the electron move into the N side and the holes into the P side. So, the recombination with the ions near the junction takes place, which in turn reduces the width of the depletion region and hence the barrier potential. Now, the electrons from the N side is accelerated towards the P side. The accelerated electrons experience a strong attraction by the positive potential applied to the P side, which results in the movement of the electrons towards the P side and in turn holes towards the N side. When the applied voltage is increased, the width of the depletion region and hence the barrier potential are further reduced. This results in a large number of electrons passing through the junction, resulting in an exponential rise in the current through the junction. When a diode is reverse biased, the P side of the diode is connected to the negative terminal and the N side of the diode is connected to the positive terminal of the battery. In this condition, a positive voltage is applied to the N-type material and a negative voltage is applied to the P-type material. The positive voltage applied to the N-type material attracts the electrons towards the positive electrode and away from the junction, while the holes in the P-type end are also attracted away from the junction and towards the negative electrode. As the electrons flow towards the positive side of the voltage source, additional positive ions are created. This results in the widening of the depletion region, which results that a high potential barrier is created, thus preventing the current from flowing through the semiconductor material. With this, let's move to the characteristics of a junction diode. The characteristics of a junction diode is the study of variation in current through the diode with respect to the applied voltage across the diode. This is the VI graph of the semiconductor device. The positive and the negative side of the axis do not have the same scale. That is, you can see that in the positive y-axis we have milliammeter, while in the negative y-axis we have microammeter. Using this VI characteristics of the diode, we can find the voltage and the current flowing through the diode, and also we can analyze the circuit containing the diode. Now, let's see the key points to plot this graph. The voltage across the diode is varied by varying the biasing voltage across the DC power supply, and the external resistance is used to limit the flow of current through the diode. The reverse or the forward bias voltage and the corresponding reverse or forward bias current are noted. And the graph is plotted by taking the voltage along the x-axis and the current through the diode along the y-axis, with the forward voltage along the positive x-axis and the reverse voltage along the negative x-axis. And similarly, the forward current is taken along the positive y-axis and the reverse current is taken along the negative y-axis. Now, let's understand the forward characteristics. The forward characteristics of a junction diode is the study of variation in current through the diode with respect to the applied voltage across the diode when it is forward biased. That is, when the P side of the diode connected to the positive terminal and the N side of the diode connected to the negative terminal. This is the circuit containing the diode under forward bias condition. After connecting the diode in a forward bias condition, we slowly increase the voltage and record the corresponding value of the diode current. We know that in the forward biasing, when we increase the forward voltage, the depletion layer decreases. At room temperature, a potential difference equal to the barrier potential is required before a reasonable forward current starts flowing across the diode, and this is known as the threshold voltage or the knee voltage. That is, the knee voltage is the minimum voltage at which the diode starts conducting and the current starts increasing exponentially. And when the applied voltage is less than the threshold voltage, the current is almost negligible. The knee voltage of some of the diodes like silicon diode is 0.7 volt and for germanium diode it is 0.3 volt. Now let's define forward resistance. Forward resistance of a diode is the ratio of the small change in voltage to the small change in the current. In the graph, we can see that the forward current being taken in the y-axis and the forward voltage taken in the x-axis. And the forward characteristics graph is plotted. We denote forward resistance as RF, and from this graph we can see that the small change in voltage is from C to E and the small change in current is from D to F. So the forward resistance RF is equal to CE by DF, which is equal to delta V by delta I, which is the small change in voltage by the small change in current. Now let's understand reverse characteristics. The reverse characteristics of a junction diode is the study of variation in current through the diode with respect to the applied voltage across the diode when it is reverse biased. That is, when the P side of the diode connected to the negative terminal and the N side of the diode connected to the positive terminal. This is a circuit of a diode under reverse bias condition. Similarly, as we did in a forward characteristics, in the reverse characteristics also, we connect the diode in a reverse bias condition and gradually increase the voltage and record the corresponding value of the current. The current remains constant at negligibly small value in the range of microamperes for a long range of change in applied voltage. When the voltage is raised above a particular point, the current suddenly shoots up and this is known as the reverse current. This is due to the flow of minority charge carriers, hence called as the leakage current or the reverse saturation current. A particular value of the applied voltage where reverse current through the diode increases suddenly is known as the breakdown voltage. That is, breakdown is characterized by the rapid increase of the current under reverse bias condition. The corresponding applied voltage is referred to as the breakdown voltage. Now, let's see what is reverse resistance. Under the reverse biasing condition, the opposition offered by the diode to the reverse current is known as the reverse resistance. Ideally, the reverse resistance of a diode is considered to be infinite. However, in actual practice, the reverse resistance is not infinite because the diode conducts a small leakage current due to the minority carriers when it is reverse biased. Now, a question arises why, unlike a resistor, we cannot describe a diode's operation by simply using an equation such as Ohm's law. This is because the diode does not behave linearly with respect to the applied voltage, and the PN junction diode has the characteristics of passing current in one direction only. That is, all the semiconductor devices are non-linear elements because the current drawn by the device is not proportional to the applied voltage. The semiconductor devices have a barrier potential, and when the applied voltage is increased above the barrier potential, the device starts conducting. If the voltage is increased above the barrier potential, the voltage across the device remains constant and the current starts increasing. This happens because the concentration of the holes and the electrons increases as the current through the device is increased. The resistance of the PN junction is not constant and does not vary with the flow of electric current through the junction. The voltage and the current has a non-linearity in the semiconductor junction diode. And also the diode has an exponential current voltage relationship. That is, the current I rises abruptly when the voltage reaches a particular value. Also, from the characteristic graph, we can clearly infer that the current flow is not linear and it is exponential. Therefore, it does not obey Ohm's law and hence we can call it as a non-ohmic material. Though the diodes do not follow Ohm's law, at any given current level, you can measure the change in voltage for small changes in current and get a local equivalent resistance called as the dynamic resistance. We denote dynamic resistance as RD, which is equal to the delta VD by delta ID. With this, we have come to the end of the session. Hope you all gained some knowledge. Meet you soon. Until then, this is Shanmaathi signing off from you.